All right, now we're going to be going over combustion reactions and how to identify when you're going to have to balance a combustion reaction. Okay, so words related to combustion reactions will be words like if you have like some substance burning, okay, or some substance has been ignited, or some substance react with oxygen. Those are all words that give you a clue that you are dealing with a combustion reaction. Okay, so essentially what a combustion reaction is when you have a fuel burning in the presence of oxygen and it's going to produce oxides. Okay, so back in an earlier lesson here, I did specify that since I was talking about a hydrocarbon, because methane is a hydrocarbon, when I was talking about a hydrocarbon plus oxygen gives you carbon dioxide and water vapor, that would be more specifically a hydrocarbon combustion reaction. But I did mention it could be any fuel reacting with oxygen, and if you have a fuel in a more vague sense of the word reacting with oxygen, that's where you're going to get your common oxides as your products. Okay, so to help you figure out which oxides are the most common oxides, we're going to make a list here. So if you have carbon reacting with oxygen, the most common oxide would be carbon dioxide. With hydrogen and oxygen reacting, the most common oxide there would be water. And I'm going to assume that these combustion reactions are going to be hot enough to produce water vapor. Like I said, the only combustion reaction that typically is not hot enough to have water in the gaseous state would be photosynthesis. Okay, if nitrogen and oxygen react together in a combustion reaction, the most common oxide is nitrogen dioxide. Sulfur and oxygen would be sulfur dioxide. And then some metal with oxygen would be the most common metal charge. So that's going to be the first charge listed on the periodic table, and then the oxide ion with that. So common metal charge, and I'm going to put charge in brackets because that's when you have, or when you've written the charge for some multivalent metal, you put it in brackets with the Roman numerals. Okay, so all of these are going to be important, so make sure you are aware of them. Okay, and over to the right here, there's a little tip with balancing combustion reactions, which is always to leave oxygens to the very end to balance them. Hydrocarbon combustion is when compounds containing hydrogen and carbon, and sometimes oxygen, they react with oxygen to form carbon dioxide, so CO2, gas. I'm going to bump that 2 up a little bit so it's easier to read, and water vapor. Okay, so basically what this is saying, if you have a hydrocarbon combustion, your products are always going to be carbon dioxide and water vapor in the scope of Chem 20. Okay, so first example, this is going to be a hydrocarbon combustion. How do you know that? Because the compound contains carbon and hydrogen. Okay, so we have butene reacts with oxygen. So some sort of fuel reacting with oxygen, that's your clue that this is a combustion reaction. Okay, so C4H8. Question specifies that it's in the gas state, reacts with, you can translate that to a plus sign, and it's also telling you that butene as well as oxygen, they are your reactants. So remember, oxygen is one of our diatomic elements, so when it's by itself, there's always two of them. All right, so as we said up above here, when you have a hydrocarbon combustion, you are going to get carbon dioxide and water vapor for your products. So CO2 gas plus water vapor. Okay. So like this note over here said, we are going to leave oxygen. So this right here, we're going to leave that to the very end to balance. Okay. Now what we are going to do to balance with hydrocarbon combustions, I like to balance in this order. Carbon first, then hydrogen, then lastly oxygen. Okay, so we got 4 carbons coming in. We need 4 carbons coming out. So I'm going to put a 4 for that coefficient there. Okay, so carbon taken care of. Now let's worry about hydrogen. There's 8 coming in, so I want 8 coming out. So carbons are balanced, hydrogens are balanced. Now we need to worry about oxygen, which I realize I did not put a state there. Okay, so just as a quick reminder, it's very important to make sure you write all the states for each reactant and product. Okay. All right, now dealing with oxygens. Okay, so right now we have 2 oxygens on the reactant side. With the product side, it's a little trickier. Okay, because right now we have 2 sources of oxygen to take into account. So right now we have 4 times 2, so 8 oxygens coming from carbon dioxide, and we have 4 times 1, so 4 oxygens coming from water vapor. Okay, so 8 plus 4, that's going to give us 12. Okay, so we're asking ourselves, okay, what times 2 is going to give us 12? So I'm going to go, well, 2 times 6, that's going to give us 12, right? Because we have the 6 and we have the 2. That's how we're getting that we need to multiply them together there. Okay, so now we have 12 oxygens on the reactant side and 12 on the product side, so everything is now balanced. All right, moving on. Carbon disulfide burns in air. So that keyword burns, that's your giveaway that it is a combustion reaction. Okay, so carbon disulfide, so carbon, and then disulfide, that means there's 2 sulfurs. All right. Now, what I'm going to do, just because this is a compound that's a little bit trickier to figure out what the state of it, typically for questions where it is a little bit tricky to figure out what the state of a compound would be. In this case, for molecular compounds, it's a bit harder. So I'm just going to adjust this question to be like liquid carbon disulfide. Okay? So just a heads up on that. This question should have been a little bit more specific. All right. So it burns in air. So that means reacts with oxygen. Now, for the products, what you have to kind of imagine is you're going to think about each element that makes up your fuel, which in this case is carbon disulfide, and be like, okay, what is the most common oxide? with that element. Okay, so I'm looking at carbon and I'm being like, okay, it's reacting with oxygen. What's the most common oxide that carbon and oxygen can form? Well, that's going to be carbon dioxide. So then that means my first product, I'm going to put carbon dioxide as a gas. Now I'm going to do the exact same process with sulfur. So sulfur reacts with oxygen. What's the most common oxide that sulfur and oxygen can produce? Well, that's sulfur dioxide. So plus sulfur dioxide. Okay, make sure I got all my states in here. All right, so now we have our skeleton equation. Now we need to balance it. Okay, so for carbons, one carbon coming in, one carbon coming out. Done. For sulfur, two coming in, one coming out. So I'm going to put a 2 right here to make sure 2's going in, 2's coming out. All right, oxygen. We have 2 on the reactant side. For the product side, once again, we have 2 sources of oxygen. So we have 2 from carbon dioxide plus 2 times 2, so 4 coming from sulfur dioxide. So 2 plus 4, that's going to give us 6. Okay, so now we got to ask ourselves, okay, 2 times what is equal to 6? Well, 2 times 3 is equal to 6. Okay, so now we have 6 oxygens on the reactant side and 6 oxygens on the product side. We are good to go. Everything is balanced. Okay. By the way, if it really bugs you to write no number in front of any reactant or product, it is assumed that there is an invisible 1. So if it really bothers you to leave it like there's no number in front of it, you can just write a 1. Okay? But if you leave it like this, I will assume that there is 1 carbon disulfide and 1 carbon dioxide in this reaction. Okay. Dinitrogen tetrahydride gas burns in oxygen. Okay, burns, that is your keyword that this is a combustion reaction. Okay, so di means that there's 2 nitrogens. Tetra means that there's 4 hydrides. So hydride is just a hydrogen with a -1 charge. Now, since this is a molecular compound, so made up of 2 or more nonmetals, the prefixes tell you exactly how many atoms of each element you need. You do not need to write the charges like we did with ionic compounds, and you do not need to do crisscross applesauce. That is the whole point of the prefixes in molecular compounds, is to tell you exactly how many atoms of each element you need. For ionic compounds, you need to balance the charges in order to figure out how many atoms of each ion you need. Okay, so this is a gas, burns with or in oxygen. Okay, so now we're going to do exact same thing that we did before. Okay, so nitrogen reacting with oxygen, most common oxide between nitrogen and oxygen would be nitrogen dioxide. So NO2 gas plus, now we're going to do the same thing for hydrogen. Most common oxide that hydrogen can form with oxygen, well, that's going to be water vapor. Oh, let's write that state right there. Okay, now we move on to balancing the skeleton equation. So we got 2 nitrogens coming in, 2 coming out. Okay, for hydrogens, 4 coming in, we need 4 coming out. Okay, now for oxygens, right now we have 2 on the reactant side. For the product side, we have 2 times 2, so that's 4 from here, and then 2 times 1 from here, so that's going to be 2. So we have 6 oxygens on the product side. So now I'm going to ask myself, 2 times what is equal to 6? 2 times 3. So now we have 6 oxygen on the reactant side and 6 oxygen on the product side. So now everything is balanced. Okay. Last example here, we have copper 2 cyanide combust. Okay, so combust, keyword that it is obviously a combustion reaction. Okay, so copper, symbol for that is Cu. That's 2+. I'm just writing that as a note to myself right now. Now, cyanide, if I look at my periodic table, that is one of our polyatomic elements. Now, let's see where it is. Okay, so cyanide is right here. So Cn, and it has a 1- charge. So the reason why I'm paying attention to the charge now is because this is an ionic compound, because we have a metal and nonmetals together. All right, so because it is an ionic compound, we can assume it is a solid because the question didn't specify otherwise, and we need to balance the charges. So we know that 2 minus 1, that does not equal 0. So we got to do crisscross applesauce. But keep in mind, we're trying to put a 2 behind cyanide. And since cyanide is a polyatomic ion, we don't want to say that there's 2 nitrogen. We want to say that there's 2 cyanide ions. So because of that, we need to put brackets. So rule of thumb, if you have more than one polyatomic ion, put brackets around the polyatomic ion and then put your subscript after. Okay, now I could write 1 behind copper, but since I wrote copper, it's already assumed there's 1 atom of copper here. All right, so let's clean this up a bit and erase that. So since it combusts, that just means our other reactant is oxygen. All right, so we need to figure out the metal oxide here. Okay, so copper and oxygen, let's check out the most common charge for copper here. There copper is. Okay, so copper is number 29. Most common charge for it is 2+ charge. Okay, the reason why I'm saying we need to figure this out with the most common metal charge is just because back in our notes we said any metal when it reacts with oxygen is going to give you the most common metal charge, oxide. Okay, so we have copper 2+ oxide. Oxygen, or sorry, an oxide ion likes to have a 2- charge. The reason being is because it is part of group 16, and group 16 ions like to have a 2- charge. Okay, so since 2 minus 2 is equal to 0, we don't need to do crisscross applesauce. Okay. Now, since this is an ionic compound, we can assume it is a solid. All right. So we're just going down the line here with our first compound, this copper 2 cyanide, and we're just saying, okay, oxygen is reacting with all of these. What is the most common oxide that can form with each of these elements? Okay, so most common oxide formed with carbon, well, that's going to be carbon dioxide. Okay, so where I'm getting that information from is back in the notes right there. Most common oxide to form with nitrogen would be nitrogen dioxide. Okay, so let's work on balancing here. All right, so copper, 1 coming in, 1 going out. That's good. With carbon, we have, so it kind of looks like there's 1, but there's actually 2, because this 2 affects everything inside of the bracket. So 2 carbons coming in, we need 2 carbons coming out. Okay, so carbon's all good. Now, with nitrogen, there are 2 nitrogens coming in. We need 2 nitrogens coming out. All right, now let's figure out oxygen. So there's 2 on the reactant side. Now we have 3 sources of oxygen here. So we gotta add them all up. So we have 1 from here. We have, let's get rid of this arrow there. We have 2 times 2, so that's 4 coming from this source. And then we have 2 times 2 coming from this source, so 4. So we have 9 in total, 9 oxygens in total, oxygens. Okay? Now, here's the trick. As you can see, there's no number no whole number you can multiply 2 by to get to 9. Okay, so here is my quick little trick to get that sorted. Okay, so I'm gonna take the number, the total number of oxygens from the product side, and I'm going to put that in the numerator, and then I'm going to divide it by 2. The reason why I'm dividing it by 2 is because of this little 2 right here, okay? Because 9 over 2 multiplied by 2, well, 9 times 2, that's 18. And then 2 times 1, that's 2. 18 divided by 2, that's 9. Okay? So this does represent that we have 9 oxygens. Okay. Just keep in mind, though, that if it really bugs you to have a fraction for a coefficient, we can fix that. By the way, it's super important to know that the only type of reaction where you are allowed to have a fraction for a coefficient is combustion reactions. You are not allowed to have any fraction coefficients for any other type of reaction. Okay? So just as a heads up, since this is the only type of reaction, combustion reactions, that you are allowed to have a fraction for a coefficient, we could leave this just like this. But if it really bugs you to have that fraction there, this is what we can do. We can times everything in this equation by 2. Why are we timesing it by 2? Because of the denominator here. Okay, it will get rid of that denominator. So if we times everything by 2, this is what will happen. We will get 2 molecules of copper 2 cyanide. 9 over 2 times by 2, that's just going to give us 9. Okay, you can put that in your calculator. I already wrote out the math on this just previously. I just erased it. Okay, but we can go just 9 right there. Now the trick here with multiplying by 2 is you need to remember to multiply absolutely everything by 2. The problem that most students have is they remember to multiply by 2 maybe just for the reactants, but they completely forget about the products. So that's the tricky part about fixing your fraction. Sometimes it's hard to remember. Okay, 2 times 2, that's going to be 4. Same over here. 2 times 2, going to be 4. Okay, so again, you could have left the fraction coefficient, or you could multiply everything by 2. Okay, what I'm going to do is I'm going to be like, or we could have it like this. Okay, so both answers are correct. It's more so just a preference of, are you okay with fractions for your coefficients? But you do need to remember that combustion reactions are the only type of reaction you're allowed to have a fraction for. Or if you would rather have whole numbers for all of your coefficients, you need to remember to multiply every single reactant and product by 2. So that's the trick. You can choose either or fractions or no fractions. Just remember to apply the tricks like multiplying everything by 2, or knowing that combustion reactions are the only type of reactions where you are allowed a fraction for a coefficient.